All right. Uh, Hello, class. Hope you're doing well. Hope you're having a nice weekend. Um, Technically, it's still the weekend. It's Memorial Day. Uh, but I kind of forgot about that until I had already announced that we were having lessons. So I'm just going to go forward with my lesson. Um, a couple of announcements. First of all, we're going to have a meme review on Friday, so please submit your memes. This will be the last meme review. Also, I'm going to post a quiz by the end of the day today that will be due on Friday. That will be your last quiz. There will be no more homework questionnaire. Friday's homework questionnaire was the last homework questionnaire. So yeah, that's where we're at. Let me see if I'm forgetting anything else. I think that's it. So today's lesson is going to be qualitative. So there's no daily item for today. I'll try to keep it pretty quick. But I wanted to talk about where do you submit what? If you have a meme, you submit it on the Discord page. As far as the quiz, you email it to me. And Michael, I got a message from Mr. Easton about possibly doing an extended essay in physics. So we should talk about that in the next week or two. So I'll be contacting you. All right. So what we're going to talk about today is cosmology. All right. If you don't have the Discord, you could email them to Rourke Chow or Justin Weiler. Those two kind of are the meme people. They're not mean people, they're meme people. Hey Christian, thanks for joining. So we're talking about cosmology, and cosmology is basically the study of the universe as a whole. So, past, present, future, okay? So if we so one of the first things you should know about cosmology is that cosmologists believe, so the universe is expanding, right? Right now the universe is expanding, and I mentioned that with Hubble's law. Galaxies that are farther away from us are headed away from us at a greater rate. So that's evidence for the universe itself is expanding. The fabric of space-time is expanding. And so if the universe is expanding into the future, then that means if we go to the past, it must have been smaller, okay? And in fact, we've managed to rewind the video sort of all the way back to the beginning. And so we believe that, or cosmologists believe that there was an event called the Big Bang. And the Big Bang was when the universe began, okay? Now, as far as we know, we can't see the entire universe because we can't see the entire universe because it takes light time to travel across the universe, okay? So we can't see the whole universe, but as far as we know, the universe is infinite. if we could see it all, it would just be infinite. And so with the Big Bang, the thing you have to understand with the Big Bang is that before the Big Bang, we don't know. Okay? After the Big Bang, it was already infinite. So it was like the universe came into existence with the Big Bang, and it was already infinite. Now, when I say the universe is expanding, I mean that the universe is becoming even more infinite. Okay? So basically what happens is if you were to look at, let's say that this is the fabric of space-time, okay? So the fabric of space-time was already infinite, okay? But in the future, the fabric of space-time is now getting more infinite. You can think about it as the threads are getting further apart, okay? So it goes from infinite to even more infinite, okay? So maybe this is today, all right? So when we rewind the video back, what we find is that the universe, so we can rewind and we can see when was the point at which the explosion happened. And as far as we can calculate, it was about 14 billion years ago. Okay? And so 14 billion years ago, the universe came into existence and was endowed with a lot of energy. Okay? So that energy is what fueled the expansion, because you can't, the fabric of space-time is a bit like a rubber sheet, and in order to stretch the fabric of space-time, you have to have energy. Okay? So we don't know where that energy came from. We don't know if it even makes sense to talk about what was before the Big Bang. But yeah. So in the Big Bang, there's a ton of, the universe came into existence. There was a ton of energy given to it. And so the universe was filled with energy, okay? And the form that energy was taking was, photons, basically. And then, according to E equals mc squared, all right, pure energy, like photons, can turn into massive particles. So basically, the photons, some of those photons converted into massive things, all right? So they converted into, quarks, leptons, but those leptons were not, or the quarks weren't bound together into nuclei, okay? They were just random quarks bouncing around, random leptons bouncing around. Then, the quarks started to form nucleons. So now you have protons and neutrons. And then after that, you start to have nuclei and atoms are forming. So as the universe is expanding, it's cooling, and the more it cools, basically we're able to get, the universe is able to turn into more and more like we know it today. Okay, so the early universe was just way too hot. It had way too much energy to have atoms. Okay, it was too hot for atoms. The atoms would just turn back into photons. And then it cooled down to the point where, okay, we can have matter, but it's going to be quarks and leptons only. And then it cooled to the point where the quarks could turn into nucleons, and then the electrons could bind to the nuclei. Okay, so I can't remember exactly how much time this took to go from just pure energy to atoms, but I don't think it was very long. It might be something like, seconds. It's either, I can't remember exactly how long it is. So now you have a universe that's made of atoms, and then what happens is those atoms start to gravitate towards each other, and you have stars. Okay, so you have the first stars are born, and then you have those stars are merging to form galaxies. So basically, we have a progression of only small scale structure to larger scale structure. Okay. So what are the key pieces of evidence? For the Big Bang. So one piece of evidence is that the universe is expanding. And so that is expressed in terms of Hubble's law. So that's one piece of evidence. Another piece of evidence is something called the cosmic microwave background. Oops. Also known as the CMB. And basically the cosmic microwave background, see how when the Big Bang happened, the universe was filled with photons. All right? Some of those photons merged to form quarks, leptons, and so on. But not all of them. And it turns out that those photons, some of those photons are still roaming across the universe, okay? And most of those photons these days are of a frequency that would put them in the microwave part of the spectrum. And so we are actually able to see the microwaves, the microwave photons left over from the Big Bang, okay? So we've seen it. Basically, the cosmic microwave background is the leftover flash of the Big Bang, if you will, okay? It can still be observed, okay? It's still out there. So that's pretty cool. Another thing is something called Olbers Paradox, which I think is kind of neat. If you think about it, the universe, what if the universe was infinitely old? Okay? What if the universe was infinitely old and didn't have a finite age? If the universe was infinitely old, then the night sky would be bright. Why do I say that? Because, if the universe is infinite in size and infinitely old, then light from stars, basically any direction you look in the night sky, you would see a star, right? Because the universe is infinite, okay? So, if you go along any direction, eventually that direction is going to run into a star. And if the universe is infinitely old, then the light from that star has had time to reach you, okay? So every point in the night sky, if the universe were infinitely old, every point in the night sky would have light. So the night sky wouldn't be dark. It would be like daytime. And so the fact that the night sky is dark implies that the universe has a finite age, which implies it has a beginning. Okay? So this is the Big Bang. If you want to know a lot more about this process of going from photons to the universe as we see it today, I would recommend reading A Brief History of Time by Stephen Hawking. Okay? So we could talk about the fate of the universe. So what is going to happen as the universe goes on? One thing that astronomers or astrophysicists have done is they've made some graphs where basically they graph the size of the universe. And as I said, the universe is infinite in size, but what I mean is, if you just took a square of space-time and you looked at what is the size of that square of space-time, I said face-time, as a function of time, okay? And so size of the universe versus time. So this would be a universe that forever expands. This would be a universe where it expands, but the rate of expansion slows to 0, and so it reaches a constant size. This would be a universe that the expansion accelerates, so it spreads apart faster and faster and faster. This would be a universe where the size of the universe reaches a maximum and then it comes back down to size 0. So all of these are possibilities, all right? There's different fates of the universe. This fate is called the Big Rip. Okay? The Big Rip. And so basically, in this scenario, the size of the universe is actually accelerating. It's getting bigger and bigger at a faster and faster rate. So eventually everything just gets really far apart. Okay? This option right here, where the size of the universe reaches a maximum and goes back to 0, is often called the Big Crunch. So in the theory of the Big Crunch, the universe is going to reach a maximum size, and then the video is going to come back down to size 0. Okay? The Big Crunch, when I first learned about the Big Crunch makes the most sense to me. Because gravity pulls things together. So it makes sense that that this would happen. It also makes sense that this could happen. Maybe the universe gets so far apart that gravity can't pull it back together in time. So it's kind of like you have a universe that reaches a terminal velocity. So that one makes a little bit of sense to me. The Big Rip does not make any sense to me at all. Okay? One other thing I wanted to talk about. So there are some theories that think maybe the Big Crunch, where the universe comes back down to 0 size, maybe right when the Big Crunch happens, it bounces. And it does something like this. So the universe repeats itself in a cycle. This is called the Big Bounce. Okay? So there are all these possibilities for the fate of the universe. It actually turns out that the evidence points to the Big Rip. The expansion of the universe is accelerating. Okay? So what is the main evidence for the accelerating expansion of the universe? Because that's just crazy. The gravity would tend to slow down the expansion. Basically, the main piece of evidence is that distant supernovas are dimmer than we expect. Okay? So we look at supernovas that are way far away. And because they're way far away, we're basically looking at supernovae from the early universe. Okay? And as I mentioned in an earlier lesson, type this is type 1a. So type 1a supernova are the ones that have standard brightness. Okay, so we can figure out type 1a supernova, and what we find is that they are dimmer than we expect. Okay, and so the only way that they could be dimmer than we expect is if space-time expanded at more than a constant rate. Okay, so there's some kind of effect going on where the amount of space between us and the supernova is accelerating. Okay, and because the amount of space is greater, the supernovae appear dimmer. Okay, so a couple years ago, or maybe it was a decade ago, actually, it might have been. There was a Nobel Prize for this observation. And so basically, in order to expand the universe at an accelerating rate, you need energy. Okay, and so the source of energy to accelerate the expansion is called dark energy, because we can't see it. We don't know what it is, where it comes from, but it's there. Okay? So dark energy is a huge mystery. And it's accelerating the expansion of the universe. So we don't know what it is, where it comes from. So this is really a placeholder name for dark energy. If you were able to pin down what exactly is the origin of dark energy, then it's an instant Nobel Prize for you. Okay. Michael Judson asks, is there infinite mass in the universe? I suspect yes, because now remember, we can only experimentally see part of the universe. Okay. So, but one of the properties that for the universe that we can see, the universe is homogeneous and isotropic. So what do those two terms mean? Homogeneous means that basically the universe has the same properties everywhere. Okay? The galaxies over there are no different than the galaxies over here. So all the galaxies are, no matter where the galaxy was when the universe started, they all seem to have more or less the same properties. So that's called homogeneity. So if the universe is truly homogeneous, then it would be infinite, right? Otherwise, the galaxies on the edge would be different than the galaxies in the middle. And then isotropic, that's the property that every direction we look, there's not any fundamental difference. There are different galaxies in each direction, but on the average, the universe is pretty much the same in every single direction we look. So the universe, as far as we know it, is homogeneous and isotropic, which means that basically every point in the universe, no point in the universe is special. Okay? And so based on that, I tend to think that the universe is infinite, and so therefore it would have infinite mass. If the universe was finite in size, then it would have finite mass. It would be a very large mass, but it would be finite. But you have to remember, we can't see the entire universe because it's only been around for a finite amount of time. So the light from those distant stars hasn't gotten to us yet. And when it does get to us, it might be too dim to really see it. So there's some issues with that. So dark energy is a mystery. Now, one of the things that we've done is we've used E equals mc squared. And we've basically taken, remember, I talked in a previous lesson about dark matter. So they took the amount of dark matter and they converted it to an energy. Okay? And then we also did that with the regular matter in the universe. So protons and neutrons and electrons and so on. And we converted that to an amount of energy. So basically, the three major constituents of the universe, dark energy, dark matter, and regular matter, we put them all on the same scale. Okay, we converted them all to units of energy. And when we do that, we get this pie chart, which is in the lower left-hand corner. And what it says is that most of the energy in the universe is dark energy. Most of the stuff in the universe is dark energy. Almost 3/4. And of the remaining quarter, the vast majority of it is dark matter. So this is really bizarre. So the regular matter only makes up about 4% of the universe on an energy basis, which is just crazy. So, because regular matter is the stuff that we understand and observe. So most of the universe is made out of stuff that we can't see or detect or understand. So there's, so I actually think astrophysics is one of the, is one of the great mysteries of physics, because I think a lot of the discovery in the future is going to come from astrophysics. We're so limited on Earth. We're limited in the size of the experiments we can do. We can't do experiments with black holes, but we can observe black holes in the cosmos. Okay, so the universe has, if we look throughout the universe, we can see extremely rare events that we don't have the ability to replicate on Earth. So astrophysics is a great field. So this is a great mystery. Another great mystery that I'll talk about just really briefly is matter-antimatter asymmetry. Okay? Why is, as far as we know, the universe is filled with matter and very little antimatter? So why is that? We don't know, because the universe tends to be very symmetrical, right? I said it's isotropic, it's homogeneous. Why isn't it matter-antimatter symmetrical? Why aren't there equal amounts of each? But the observable universe is pretty much entirely matter. So that's another thing. There's all kinds of mysteries in astrophysics. So anyways, that's my lesson for today. Tomorrow we're going to talk a little bit about relativity. And then that'll be the last two lessons, and we will conclude.